So what is key-based encryption? Key-based encryption is the alternative to using an encoder and a decoder. With this, the major problem with having an encoder and decoder is that we don't actually know at any time if Eve has actually gained the encoding decoding algorithm. So an improved method is to have a standard algorithm that everybody knows about, and then what we do is use a special key to apply to the algorithm, and the key is fairly difficult to find so that Eve cannot find the key. The key could be shared between Bob and Alice in this case and kept secret so that Eve cannot find out. So in this case we take the plain text into ciphertext. Eve doesn't know the key, even though she knows the algorithm. It's sent to Alice, and Alice can then decrypt it with this special key. The main methods, as we'll see, are defined as symmetric encryption. With symmetric encryption, Bob and Alice use the exact same key to encrypt and then to decrypt. We'll also look at asymmetric encryption, where we use a different key to encrypt and to decrypt. And then there is a special encryption method called a one-way hashing, in which we can transform a message into what's defined as a hash message. The methods that we'll look at here for private key include RC2, RC4, DES, 3DES and AES. For public key, we'll look at RSA. For hashing, the two main methods are MD5 and SHA1. So the key thing we need to know is that how safe is our key? How big should our key be? How complex should it be? So let's look at an example where we have 4 notches in a key, and the notches can either exist or not exist. How many keys can we have in total? Well, we can have 2 to the power of the number of notches, or in this case 16 different keys. If we represent this in binary format, a key without any notches is all zeros, and a key with all the notches is all ones. So we can see here that it wouldn't be too difficult to find the key because there are only 16. So it is obvious to keep something secure that we need to limit the number of keys. We need to maximize the number of keys that are available. Just to show you the scales involved of these, let's say that each one of the keys of a 64-bit key measured 1 millimeter. Let's say that we had each one of these physical keys was 1 millimeter in length, and we laid them all alongside each other. For 64-bit, how big would that total length be? The width of Napier's campus at Merchiston, the width of Edinburgh, 6 miles, the distance between the Earth and the Moon, about 93 million miles, or the width of the solar system, or the width of the Milky Way. Okay, so we have 2 to the power of 64 keys, and if we had physical keys, each of them were 1 millimeter, how long would it actually be? Well, amazingly, it would be somewhere between the size of the Milky Way and the universe. In fact, it would be this long, somewhere between the Milky Way and the universe. So we're dealing with extremely large numbers.